underway. Um, then what I wanted to do was I don't really have any major critical announcements or anything like that. Um, I the the three quizzes are up. I do have to go back and add the time for accommodations on those quizzes, so I'll be doing that in during my office hours, basically. Next up is there's two activities that are up. One of those activities is dealing with molar mass conversions, and that's something that we're going to get into on Wednesday. So if you want, you can read ahead on that if you want to go ahead and get started on that activity. Um, Otherwise, just if you start doing that, you're like, oh my gosh, what do I do? We'll get to that on Wednesday. And we're going to go through, Wednesday's lecture doesn't have a huge number of slides instead, or in the slide deck. Instead, mostly what I'm focused on for that is some practice problems. I think there's like 16 slides in the slide deck. Because I want to make sure that everyone feels like comfortable and confident in that. Um, Okay, so I just got a private message. People in the group me saying they're having trouble joining the Zoom link or logging in. They have to use their Texas State credentials. Um, and I'm not exactly sure what the specific problem is there. Um, so if you could, if someone's texting you or something like that, could you kind of relay that? Um, yeah, the SSO button, pass that on. That would be that's I think, yeah, that should be the thing that is triggered when they click the link. But if it's not, that's what they need to do. And I will go ahead and I will add an announcement real quick. Make sure you are using the SSO link, or make sure you are joining. Make sure you uh, group chat is texting. Two people said they email you and their the TX state thing isn't working. That sounds like they need to contact ITAC if they're having issues with their Texas State account. Um, okay, so here we go. And that sounds like I'm completely dismissing them, and I'm not intending to dismiss them. But this is how it's set up so that we can get people who are in the class to join, and how people aren't joining as iPad 4 or iPhone. So it's possible that it's the SSO button that they have to click. They have to go through their SSO, secure sign-on. Okay, so this is being recorded. They'll have access to that. I had some questions, actually. I do one other announcement. I had some questions about the discussions. So the discussion is only if you cannot make it to the lecture today. So if you're encountering technical problems and you don't make it to answer any of the poll questions, then that's when you would do the discussion. I'm planning to post the discussion today by 5 p.m. or so, and then just complete that within 24 hours of our class period. And what I'm looking for is basically just a similar sort of response to what we did last time. You should go ahead and kind of be thinking about, like, what is a good multiple choice question that I could ask? Because what I plan on doing is pooling those questions and then giving them to you guys as like, hey, I've looked at all the questions and here's some that I think are really good ones. Excuse me. Um, and those will be useful for studying for your exam. Second thing after that, related to your exam, I'm going to be giving you review documents probably before the end of this week. I'll have a practice test up so that you can kind of work through some of the problems. Um, for those of you who completed the survey, the weekly survey, I'm planning on doing that every week. So anytime that you have something that you would like to add, I'd really appreciate that. Um, the feedback that I got so far, it seems like more than half of the class is feeling like confidence in their um confidence in the material is at like a 4 or 5. Um, I'm going to try to continue doing that just so I can get that feedback. So then if there's something that did not work during the week, I need to know so then I can be like, okay, well, that didn't work. So I probably need to adjust how I test on that or, be responsive. Um, yeah, there's some requests in the chat for the group me link. Go ahead and add that there. Um, but anyway, yeah, I'm going to kind of be sifting through the data that I got from your surveys, and I'll make some adjustments accordingly. It seemed like lots of people were looking for how am I actually going to be tested on this? And so I'm going to get into those. Okay, so here we go. Scientific laws. We're going to be talking about scientific laws, and these are some of the like important laws that kind of govern people's understanding of chemistry. And so the first thing that I want you to do when you're looking at this is we've got on the left-hand side, before a reaction, we have, oh, no, wrong button. We've got the before reaction. We've got this is called an Erlenmeyer flask, or sometimes it's known as an E flask. And that Erlenmeyer flask has a solution in it, and it looks like it's maybe 50 milliliters or so. And then we've also got a kind of, what would that be? It's like an amber colored solution, and this is a grad cylinder. This grad cylinder looks like it's about a 50 milliliter grad cylinder. And so our before reaction has these two solutions and these two pieces of glassware sitting on this digital balance, and we have a total mass of 173.64. Then what somebody does is they pick up that grad cylinder and they transfer it on, and they transfer the solution to the Erlenmeyer flask. Now, first things first, why did they go from the graduated cylinder to the Erlenmeyer flask? Why didn't they pour the solution from the Erlenmeyer flask into the grad cylinder? What problem would that have presented? It would overflow. You're absolutely right. Okay, so first things first, good decision there. Now, second thing, what do you notice about the kind of pigment or the intensity or um, yeah, I feel density of this solution, the darkness of this solution versus this solution? I mean, it looks to me like that the solution in the Erlenmeyer flask, yeah, it's thicker, it's denser, it's darker. Absolutely. So, this statement of after reaction kind of sounds to me like, yeah, an actual reaction took place. And based on the color, then probably. Because how would this solution on the right-hand side get darker? Well, if anything, if you poured this in and there was no reaction, well, then this amber color would get more faint, but it gets darker. So that's one indication, hey, maybe a chemical reaction took place here. And, those words of after reaction is also a good indication that a chemical reaction took place. Now, what is also worth noting here is that both of the pieces of glassware were left on there. What would happen if someone transferred the solution from the grad cylinder to the Erlenmeyer flask and then took the grad cylinder and just set it right here? What would be a difference that you would notice? I mean, the first thing is you wouldn't see the grad cylinder on the digital balance. But what's the other thing that you would notice about these two pictures that would make them different? Thinking about the instrument that's used. Exactly. The differences in the mass. This one on the right-hand side, it wouldn't read 173.64. It would read, 120 or something like that. Now, after that, that brings us to basically our important point here. our masses are the same. So, when we think about what was done here, the solution from the grad cylinder was added to the Erlenmeyer flask. Okay. The everything that was on the digital balance here is on the digital balance here. So we didn't take anything off. Now, in addition to that, well, one thing that we can say is since our mass didn't decrease, there probably wasn't a gas that was produced. But then, since our mass didn't decrease and it stayed the exact same, well, another way to use or another way to describe that is to say that the mass was conserved. We didn't see a drop in mass. We didn't see the mass increase. Sure, something new was produced in that chemical reaction, or we speculate that something new was produced there, but if it was, it didn't cause the mass to change. So what we have here is what's known as the law of conservation of mass. And I think that you probably heard this phrasing before, and you maybe heard some interchangeable terms, but like matter is neither created nor destroyed. Sort of like energy is not created nor destroyed. So matter is neither created nor destroyed during a chemical reaction, and the beaker contents changed, but the total mass remained the same. So we transferred one solution to the next, and yeah, it looks different, but we didn't produce something out of nothing. Instead, we had a reaction take place. Now, in this case, it was a liquid and a liquid that mixed together, and their total mass was the combined volume or the combined mass of the two. Then we've got this right here. This is a little bit of a different situation. We've got this solid right here. This is a solid known as mercuric oxide, and that has the chemical formula of HgO. Now, if you take mercuric oxide and you put it in a test tube, as is indicated here, and you put that test tube over a Bunsen burner and you expose it to heat. If you heat it up, basically, you put it under a flame. What will happen is that 100 grams of mercuric oxide will give you 92.6 grams of mercury and 7.39 grams of oxygen. Now, this oxygen is O2 or oxygen gas. Now, in order to do this, you're going to have some amount of mercury, Hg2, and then you're going to have that right there. That would be what's known as a balanced chemical reaction. But we've got those two components that when they're exposed to heat, that oxygen evolves and is produced as a gas. Okay. Now, go ahead and add to the chat a thumbs up, a yes, or a or a Y, the letter Y to confirm yes. If you were ever in 5th grade, or 3rd grade, or 7th grade, or 9th, or 11th grade. Okay. I'm seeing lots of yeses. I saw 1 year, and I think that works as a yes as well. I mentioned all of those grades because I remember, like, specifically in those different grades having one, like, experiment. And that was this. And in, like, 3rd grade, it was just like, oh, wow, look at the bubbles. Then in 5th grade, it was like, are there lots of bubbles? And then in 7th grade, it was like, can you design your own volcano that makes lots of bubbles? And it was like, wow, we were really nailing this one volcano experiment hard. So maybe in like 9th or 11th grade, if you did this or if you saw this, you were asked maybe about the input. Does anyone remember the ingredients aside from the paper mache or the clay or whatever was used to make the volcano? Baking soda. Done. Baking soda and vinegar. Okay. Now, exactly. Boom. And then, sometimes if you had a teacher who was like, I'm going to go above and beyond, I'm going to add some food coloring. And you'd get like, oh, like an orange lava or red lava. I mean, that was just like, that was peak stuff right there. Now, we've got our input. So baking soda, not to be mistaken with baking powder, which I do anytime I bake something. Baking soda is commonly known as a base. Vinegar is an acid. These are just classes of these two substances. We've got a base and an acid. Now, does anyone know what is produced from mixing an acid and a base together? Okay, a gas, done. And one other one, water. Now, a in this case, like if you poured vinegar on an open wound or something, it's gonna hurt. In part because vinegar is an acid. Don't pour vinegar on an open wound. Um, then if you were alternatively to look at the bottom of this volcano and see the solution that's left, well, that's going to be water. So in this case, we're going to produce CO2, gas, and water. And then one other thing, which we'll get into later on this semester, is salt. And I'll go ahead and share this joke with you right now because I will revisit it later. Um, and that is, what's a base? Well, baking soda is a base. What's an acid? Well, vinegar is an acid. And in that sort of reaction, you're going to get water and a salt. What's a salt? A crime. Is that with all bases? That's a great question. Yes, but and lol, thank you. Um, so in when you mix an acid and a base, it's called a neutralization reaction. So in a neutralization reaction, which again we'll dive into probably in end of March, beginning of April, you'll get these two things. You'll get water and a salt. And so, go ahead and continue sitting on the edge of your seats until that day whenever I bring up acids and bases and water and salts so that I can deliver that dynamite joke again. Um, but yeah, there we go. Okay, so that's like this captures the law of conservation of mass because if you were to go ahead, Lisa. That's a great question. So if you had um I'll just use general terminology or I'll use like not specific numbers. If you had a lot of baking soda and a small amount of vinegar, you're gonna make CO2 and you're gonna make water, but you're still gonna have baking soda left over. This is one of the reasons that lots of people refer to like and we'll get into this later on, balancing chemical reactions. Um, they'll refer to that as kind of like it's almost like a recipe guide or a recipe list or a cookbook because you have a good ratio, an ideal ratio of two reactants. And those will give you an ideal ratio of two products or however many products. Does it have to be equal parts? The thing is, they will react in equal parts. Whether or not something is left over depends on ultimately your total amount of input. Does that answer your question? I guess, sorry, to answer your question as a yes or a no, um, to get a product, no, it does not have to be equal parts. Okay. And this is one of the things in this class that I think will make a little bit more sense when we get into balancing chemical reactions, which is a little ways down the road. Okay. Um, okay, cool. So next up, we have what's known as the law of chemical combination. Okay, so this law is basically about if you have different elements, they can coordinate and, sorry, they can arrange themselves in different ratios. For example, um, or sorry, the law of chemical combination says that let's go with vinegar. Vinegar will react with, um, let's say, baking soda. And all of the atoms that make up vinegar, which for now I'm just going to make it simple as that, and then baking soda. Let's just imagine baking soda is this and this. Um, what could result is these things will come together and they will completely combine, and you'll get a model that looks like this. Okay. So basically, these two reactants, they combine. Um, and that's basically, simply put, that's the law of chemical combination. Things will combine together to produce a product. Now, what's with the law of chem or conservation of mass is that whatever our input is, they will kind of rearrange and combine to give us kind of a set series of products. Now, I have a whole question. Am I ready for that one yet? Then we also have the law of definite proportions. So right now we've got three laws. Conservation of mass. That means whatever your input is and your output, the amounts are effectively going to be equal to one another. So even when you don't use all of something, that's still, well, it's not destroyed or anything like that. So going back to that situation where we had a lot of baking soda and a small amount of vinegar, well, if you had 10 grams of baking soda or 10 units of baking soda and 1 unit of vinegar, well, you might produce 1 unit of O2 and water, and then you're still going to have 9 units of baking soda left over. Um, so that's our conservation of mass. Law of chemical combination says that reactants will react with one another and will produce something from that. This law of definite proportions is really something that is the wording for it is much more technical than it actually is. And we've got a poll question coming up in just a few moments. But think about any chemical that you know or have heard of the formula for. And to me, the easiest one to think of is water. Add to the chat what the formula for water is. H2O. Perfect. That's something that I don't know, when anyone probably first learned about that. I feel like middle school or something like that. You might not have known about the chemistry of it or anything like that, but you knew H2O. It fits its way into like pop culture as well. Now, every single person here said H2O. Whether you're from Seguin, whether you're from El Paso, Northern California, Belarus, um, then this is one of my favorite countries to say the name of, Azerbaijan. Um, it was El Paso. How about that? Shout out El Paso. Um, it was H2O. No matter what, water is always H2O. Does drinking water have stuff other than H2O in it? Absolutely. But does that change the formula of H2O? Belarus, shout out Belarus. No, it doesn't. Absolutely. It never does. So that's our law of definite proportions. We can define different chemicals by this is your proportion. Water will always be 2 hydrogens, 1 oxygen. That is the formula. Go. Now, with that in mind, can anyone think of something that maybe they've heard of that has hydrogen and oxygen, but is not H2O? Oh, glucose. Perfect. I see a question. Is it possible to get an absolute pure water? Yes, it is. Um, in chemistry labs and in different places. Actually, the process that you can get pure water is the same process that's used for getting or for making um, like bourbon or whiskey. It's distillation. Basically, what you do is you heat it up and you capture the water vapor. If you got tap water, actually, here's a good example. If you got tap water and put it on your range oven and just boiled it, what's going to happen? Well, the water's going to evaporate. It's going to change from the liquid water to gas. Now, what's going to be left? Can you describe what's at the bottom of your pan that you're boiling the water in? It's going to be kind of chalky, and that's going to be calcium. In Central Texas, that's going to be a big part of it. Calcium, there's also going to be sodium. Like, really, what you could do is you could get water and put it on a burner, evaporate off the water, and be left with some salt that you could then put on your noodles or something. Um, okay, so I got some good answers there with compounds that have hydrogen. So I'm going to write this up here. Has hydrogen or oxygen, but is not H2O. Okay. Now, one that I love that you guys put, they'll say you put hydrogen peroxide. Hydrogen peroxide is H2O2. Okay. Well, that's got H2O, but the thing is, structurally, this does not look like water. And tastely, if you drank hydrogen peroxide, you can feel pretty sick. I think that's what people use to like make their dogs throw up whenever their dogs like get skunked or eat something. So don't do that. And also don't make your dog do that. Not a veterinarian, not really skilled to do anything except feed and walk dogs. So not authority figure. Please do not take this advice. Okay, so H2O versus H2O, and then I'll throw on versus CO2. Thank you very much for that, Lisa. And I also saw glucose, which is C6H12O6. Now, these all have oxygen or hydrogen, and those are just those atoms rearrange and make up different compounds. This illustrates what's known as the law of multiple proportions. So we've got these different ways in which atoms and elements, or sorry, atoms of elements kind of rearrange and reconfigure to make different compounds. All right, now, just as a little bit of an example, just a second. You gotta come say hi to my friends, though.
Hi.
No, you gotta say hi. Okay. Everyone said hi back to you.
But why are those dots?
Oh, those are chemicals.
Oh.
Okay. All right, say bye-bye, everyone. Good luck on your test. He said it. That was my son, one of my sons, Arlo. Thank you. Thank you. He did. He did. He did. He said it kind of quietly, but he did. So there is law of multiple proportions and definite. Yes, I had this private question of there is a law of multiple proportions and definite proportions. Yes. I'm happy that you brought that up because multiple proportions basically is saying, well, you could have H2O2 or H2O. Those are different things. Definite proportions says, listen, if you have water, water is always H2O. If you have something that is a mixture of hydrogens and oxygens and is not H2O, it's not water. If you have H2O2, that is hydrogen peroxide. And that is always hydrogen peroxide. So another example we've got is carbon dioxide and carbon monoxide. So both of those have carbon and oxygen. What's the difference? Well, the number of oxygens. Okay, we've got 102 people in the house. I've got some Zoom questions. This is a bundle of Zoom questions. I got two of them, in fact. Now, here's the thing. Here's the deal. This is the deal that I proposed last time, and it's going to stand. We've got two questions. Ooh, this raises the stakes. Okay. If 100% of people answer both questions, everyone get up, put it out on the group me. 100% of the people answer both questions, then we get 2 bonus points on exam 1. Okay? So, everyone, are we ready? These questions are coming at the same time. I can give you about a minute and a half. And I'm looking for answers, not accuracy. You know what? If 100% get it right, two more bonus points. Okay? Deal? We ready? I think we're ready. Let's go. Might have to expand the window a little bit. 2 questions. You should see 2 questions. I think we can get 100% participation. We got some different answers, and that's fine. That's great. And in the event that you're like, oh man, there's plenty of times for bonus points, y'all. We're going to be good. Okay? I want everyone to think about and go after this question, though. That's what I'm looking for. Okay, we got about 30 seconds and 20. Oh man, you guys are moving fast to answer this one. We got 23 people who got to answer it. Okay, I think we're going to do it. Okay. I wonder if on the mobile device it does it differently. Okay, so I'm going to look for. Yeah, I see that. Interesting. I wonder if you have to tap the screen or something, then it pivots or it swings around. Hmm. Okay, I need 3 people. Oh, scroll down. Okay. 2 people. 2 people. 2 left. And I assure you, I'm not one of them. Okay, here's what I'm going to do. I'm just going to leave this question up for a little bit. I'll give you more time. I want to talk about it, though. Okay, we got 1 person left. So that's working. That's good. So effectively, what I'm getting at is there's 2 bonus points, pretty much. But I want to see that last person answer it, okay? Wake up! Wake up! Wake up! Okay, well, I'm just going to leave it up there for a minute. I think it will get answered. I'm pretty confident about that. Okay, so we've got our 2 questions here. Our first question is the composition of water. Okay, let's deconstruct this question using that right there. When you see the composition of water, I would say 9 times out of 10, your mind should immediately go, okay, that's a definition. So by giving a definition, then I'm going to be looking for definite proportions. Now, that's not to say that's the only way that that question should be asked, but if I'm previewing a question, test taking strategy sort of thing, where it's like, oh, okay, is there a key word? When you see composition, think about that as, okay, definition. Okay, yeah, I think I gotta end the poll. Okay, one person who didn't answer. Come on, man. Um, so I gotta end the poll, but you know what? We got 100 out of 101 people to answer this, so I feel good about that. So I'm gonna go ahead and end the poll. 2 bonus points on first exam, so that's a good place to be in. Okay, I'm gonna share the results. So I think everyone should be able to see this now. Um, we've got our first question. The composition of water always yields 88.8% and 11.2% hydrogen by mass, which illustrates conservation of mass, definite proportions, multiple proportions. Okay, when you're previewing a question like this or going through the question, think about, are there any keywords? And this question's kind of tricky because there's two words that are kind of keywords. The first one is composition. Composition should make you think definition. Definition should make you think definite proportions. Okay. Now, the next keyword, does anyone add to the chat what you think the next keyword is that I'm going to mention? Spoiler, it's not always. Yields, absolutely. Yields is a keyword that would kind of lead you toward conservation of mass. Because when we talk about a chemical reaction, we talk about reactants combining to yield or produce something. So this is a question that you kind of got to be careful. So pay attention to those key words. And the only reason that I would say, oh, well, we can stop and know that this is definite proportions is because of the fact that it's not water reacting with X yields this. Instead, it's just the composition of water yields this. Well, I'm composing, I'm defining what water is. Okay, give me a thumbs up or a yes if that makes sense after question one. I mean, we're at 55% of you, so I feel pretty good about that. Um, and I hope that that clears up any sort of mix up. I'm guessing that yields probably we got 31% of you who went down the direction of conservation of mass. And I'm guessing that the word yields is like decoy for you. So just be careful there. Um, next up, there are three different oxides of iron. Okay. Three oxides. Okay. An oxide, new word there, a new term. An oxide is a type of compound. So there are three different oxides of iron. Right there, what I want you to do is think, okay, we've got three variations of mixing oxygen and iron. 65% of you followed that and were like multiple proportions. And you're right. Those of you who went with conservation or definite proportions is a really attractive, and that was the second highest rated answer. That's a really attractive answer because then you see this ratio. And whenever I think of a ratio, I think of a proportion. And so that's one of the reasons that this is tricky. But what you need to do with this one is just to make sure that this doesn't say, well, iron X oxide is this. So when you think when you think definite proportions, really the more important word there is definite because defining, anytime you're defining a specific compound, that's a definite proportion. So I'm sorry I kind of rambled with that one, but I hope that I cleared up some confusion. So when you hear definition or definite or composition, think I need to see a definition. I need to see something specific ratios and stuff like that. Okay, now we are going to go ahead and proceed. Go back. Great job. I'm happy that everyone, we got a lot of engagement on that. So that's fantastic. Um, So now I want to introduce you to a guy by the name of John Dalton. What was the answer to number two? Sorry, the answer to number two, I'll share the results, was the law of multiple proportions. Because we had three different oxides and they had different ratios of iron to oxygen. So, multiple proportions was the correct answer. Okay, now Um, the next person or the person that I want to introduce it to is this guy named John Dalton. And I decided that John Dalton, if he were alive today, maybe would have uh, fantastic nicknames. So I came up with these. We've got Gassy J, the Logician, Lil Atomics, and an Atom Boy. So John Dalton was a brilliant guy, and I'm not intending to disrespect him with giving him nicknames or new names, contemporary names. Instead, I want to, bring him into, well, contemporary society. John Dalton was sitting around just like this one day when he said, I have an atomic theory, and I've got some ideas of this atomic theory. And first is that all matter is composed of extremely small and indestructible particles called atoms. Everything. This metal, I think it's probably aluminum, coffee mug that I'm drinking from, made up of atoms. This pen, made up of atoms. And you know what? Those atoms, you can't break them up. Then he said, atoms are just made of, or elements, I'm sorry, are made of just one type of atom that is unique to that element. Okay, that's a little bit of a tricky one, but what he's getting at there is that any element is made up of atoms of that element. Compounds are formed when atoms of different elements combine in fixed proportions. Okay, that sounds a little bit like our definite proportions and our definite composition in different proportions. Then we've got a chemical reaction involves a rearrangement of atoms, but there's no breaking, destroying, or creating of atoms. So these were all theories, are all a part of Dalton's atomic theory. And to this day, that's, been pretty well accepted. But as is the case with any and every scientific theory, it's just that it's a theory. And over time, that theory evolves. And new ideas come into play, new people contribute ideas, and we get something new out of it. So, Dalton's atomic theory, shown on the left, the four basically postulates or ideas of that. And then what we've come to know since then. If you've ever heard the term subatomic particles, add to the chat a yes or a Y or a thumbs up. Now, many of you adding yes, many of you have probably heard of what those subatomic particles are: protons, neutrons, and electrons. Now, an atom, well, that's your simplest unit, but that simplest unit can be broken down. And it can be broken down into the subatomic particles. And that's what particle physicists and theoretical chemists, that's what they work on. Nuclear chemistry is basically the idea of, or the field where you break down atoms. And so I like it. I like it. I like it. Gassy J. If anyone wants to, take that as their performance name, fantastic. Uh, if there's already a little atomics, I'm not going to be surprised at all. If I had the ambition to be a musician of some sort, that's what I'd probably go with. Um, so Dalton assumed, yeah, atoms are as small as they can get. Not the case. There are subatomic particles. So that part of his theories evolved. But before then, it was just like, I don't know, every this here cup, it came out of nowhere. I don't know. Must have been growing from the cup tree or something like that. So Dalton was really like forward thinking, was really like, hey, here's this great new idea I got. Then Dalton assumed that all atoms of a given element were identical in all respects, including mass. We now know this is incorrect due to subtleties in the subatomic scale. That one's a little bit it's, I would say it's abstract. It's tough to wrap your mind around. But basically, the idea is every atom, you know, okay, let me let me rephrase that. If I get a certain number of protons, a certain number of neutrons, and a certain number of electrons, if I get, let's say, if I got, yeah, this would be it. If I got four neutrons, if I got the subatomic particles, four neutrons and three protons and three electrons and put them together, that would make one element. That would make lithium in particular. If I added a fourth proton, didn't change the number of neutrons or electrons, well, surprise, I would be making a different atom or a different element. So this is where Dalton, it would be kind of rude for me to say where he got it wrong. But this is where it's a little bit, it's been evolved. Um, Next up, compounds are formed when atoms of different elements combine in fixed proportions. Yeah, straight up, done. That really hasn't changed. Chemists still all agree with Dalton. For example, carbon monoxide is CO. That's a 1-to-1 ratio. Dioxide is 2-to-1, carbon and oxygen. So our definite proportions hasn't changed. Um, then, and multiple proportions hasn't really changed. The chemical reaction involves rearrangement of atoms, but there is no breaking, destroying, or creating of atoms. That's still true for chemical reactions. Now, the only variation there is that I will say, well, a nuclear reaction. That is where you do break up an atom. You break an atom into smaller pieces and stuff. But a chemical reaction, you know, when we make that volcano, we're not doing anything crazy. We're not doing any sort of nuclear chemistry. We're just doing a chemical reaction. All right. So, how's everyone feeling about laws, chemical laws? Sure, everyone's got opinions about other kinds of laws, but can I get a yes, a thumbs up, a why if you're good on these? Okay, cool. So I'm going to give you some practice problems and ideas of how to mix around and come up with like a hypothetical question. Um, the poll question that I gave you, think about that as the sort of question that you would see on an exam, where it's like, I'm not going to ask you what is the definition of this. But instead, I would say, I got a private message here. Can you give us the definition of law of definite proportions again? Sure. So this is the sort of thing that you'd see on an exam question. I'll go back to where I haven't used much space on a slide. I can go back to the nicknames one, just so I'm particularly proud of these. Um, Definite proportions would be something like water, and this is an example, so I'll give a definition in just a moment. Water is H2O. So definite proportions, specific compounds have defined ratios, ratios of atoms. So, or ratios of combinations of atoms. I hope that works. Um, so that's our definite proportions where we're defining something. So, you know, that sort of question on an exam might be um, glucose is. That's a good stem for a definite proportions question because it's saying here's our compound, glucose is. Now we got to watch what follows that. But let's say it's, 32% carbon, 14% hydrogen, and let's see, 54% oxygen. And then the question would follow up with, this is an example of which law? Yeah, that's a great question. Exams are going to be mostly multiple choice. The only place where they're not going to be multiple choice is there are some questions that will be multiple answers. And so I'm going to jump ahead. Let's say that your exam had 40 questions. 5 multiple answers, maybe 5 tops, and then 35 multiple choice. So the 5 that are multiple answers, those are questions where it's like, select all that are true below. In which case, those are the questions where you can get partial credit. And I'll put some of those on the practice exam that I'll have up by the end of this week. Okay, fantastic. Okay, cool. So here we go. Now we're going to go on to talk about the periodic table for a little bit. And you know what? If you ever use Canva, well, you can probably see straight through my presentations and just say, like, I think that Joel just makes Canva presentations. You're right. You're right. I do. Because if not for Canva, we wouldn't have this guy joining us. And instead, the presentation would be a white background with black text, possibly with different fonts. Probably not. So I feel like this jazzes it up a little bit. Look at how eager and enthusiastic this guy is. Criticism, though, and I'll fix it real quick. And as soon as you see me making the change, add it to the chat. Yeah, there's a problem there. Yeah, he doesn't have any gloves on. Well, probably not part Smurf. Yeah, gloves. AI hands. Or, yeah. So, anyway, periodic table. So, in order to talk about the periodic table, we got to jog back for a second. And here's a poll question for you guys. Looking at these different models, these different displays. This one's not bonus point eligible. We already got 2 bonus points today, so we're good there. So which represents an element? And think back to give you a little bit of a reminder of some of our terms. We have an atom, compound, element, mixture. Yeah, I'll give another couple seconds, and I'm not going to close it right now, but I'll go ahead and do my explanation. So for this one, when we're talking about an element, it's kind of confusing because you might think, oh, well, an element is one thing. You're not wrong. An atom is an individual thing. So let's look down at C. I'm just going to scribble all this out. And let's say that C was only filled with those gray spheres. Those would be, that's an example of an atom. So if I gave you, which one of these is an atom, it would be just that. But an atom can also be an element. So an element is one thing. You're right. So like oxygen is an element. Now, where it gets kind of complicated is that O2 is also an element. This is an atom, and and these are atoms. So the correct answer for this, or the answer that I was going for, was, the answer that I was going for is the correct answer, is B. And we got a total of 55% of the class. Now it's going up. Um, we've got 57% of the class who said B. You're right. I think that one of the places where it gets kind of mixed up is that some people probably saw C and were like, oh, those gray spheres, that's an atom of an element. I'm going to click that one. Yeah, fair enough. But when you look at this right here, this is intended to be a water molecule and not a mushroom from Super Mario Brothers. Um, that is two different elements. So think about elements as having an identity or a being an identity. So this has an oxygen and two hydrogens. So those are two different elements. Now, on the periodic table, when it comes to all of the different things that are on the periodic table, you'll see something like this. You'll see, well, an atomic symbol, or a chemical symbol, I'm sorry, an atomic number, which is represented by the single capital letter Z, and an atomic mass, or an average atomic mass, or a weighted average. Now, add to the chat what you notice as a difference between the atomic number and the atomic mass. I mean, first of all, they're not the same number. Done. But what do you notice about those two numbers? And yes, one's in blue, one's in magenta. One's a decimal and the other isn't. Perfect. So that's one thing that I really want you to take home is that your atomic number is a whole number. Okay. Your atomic mass, well, that's a weighted average. So I'm going to introduce a term here that we're going to revisit on a week from today. This is an isotope. Okay. Now, an isotope is one, it's the name of the baseball team in the TV show The Simpsons, the Springfield Isotopes. It's also the name of the minor league baseball team in Albuquerque, New Mexico, the Albuquerque Isotopes. And what an isotope is, I always like to draw comparisons. So an isotope is an atom, or let me say isotopes are atoms of the same element with different numbers of neutrons. And as kind of a continuation of that, they have or also have different masses. So that number gets, or that gets kind of tricky. We're going to get into it again a week from today. But the way that I always like to think about it, because I think best with kind of comparisons and parallels and analogies, is let's say that you got a golden Oreo or a golden double stuff Oreo and a regular double stuff Oreo. And this isn't really controversial opinion or hot take or anything like that. So if you have controversial opinions about Oreos, just a second, we'll have time for that later. But my question for you guys, and add to the chat, are these both Oreos? Yep, they are. They are both Oreos. Are they different? Yes, they are. Do they have different tastes? Yeah, they do. Isotopes, think about a golden double stuff Oreo and a regular double stuff Oreo. as being isotopes. They are the same, but they're a little bit different. Now, I can't really draw a good parallel in terms of the number of neutrons or anything like that, but they are the same, but they're different. That's kind of where I'm getting at. Now, if you wanted to look at things with different masses, you could say, okay, a regular double stuff Oreo and a regular non-double stuff Oreo. Are they going to have different masses? They are. So when it comes to calculating the mass of them, let's go ahead and do that. Let's say that you decided to go to the grocery store and buy out all of the regular Oreos and all of the double stuff Oreos, and you wanted to calculate the average mass for those Oreos. Well, are these two, add to the chat, are the regular Oreos and regular double stuff Oreos going to have different masses? They absolutely are. Are they both going to be delightful? Yes, they are. Are they both going to be a wonderful vegan treat? Yes, they are, because they have no animal products involved in their production. So that's a little factoid I like to bring up as much as possible in every conversation. These two things are going to have different masses. These are great examples of isotopes with different masses. So if you said, okay, well, there's, you know, 65% of the Oreos at the grocery store are regular Oreos, and that means 35% are double stuff Oreos. And let's say that a double stuff Oreo has a mass of 2 grams and a regular Oreo is 1 gram. Your mass, your average mass for these two is probably going to be like 1.76 grams or something like that. You're taking into account the total number of them and their individual masses. Like I said, we're going to tackle that next week. Next Monday, in fact. But I want you to have this term isotope as something that is like a general definition. Two things that are the same, but they're different. Okay. Your atomic number is a whole number. Your average atomic mass is going to be a decimal number, and then you're going to have a chemical symbol. Now, as we proceed through this class, we'll get to know the periodic table a little bit more. One of the things that I want you to know, one of the facts that I want you to take home from today is that the periodic table is arranged in terms of their atomic numbers, so they're whole numbers. Um, and their chemical and physical properties are what we have as the kind of contemporary periodic table. So the current periodic table. Now, if we go back here and we look at the average atomic mass, or the atomic mass, do the atomic masses generally increase as you move along the periodic table? They do. Are there some instances where, like cobalt and nickel, cobalt's atomic mass might be a little bit higher than nickel, and we'll get to that later on. But what I want you to know today is the organization of the periodic table is done by atomic numbers, chemical and physical properties. Then the other thing that I wanted to say before we part ways is that we will, on your exam, you'll have a periodic table. Um, there are some elements that we're going to talk about more than others, but they're not going to be the sort of thing that is like, I'm not going to spring thallium upon you and say, what is the symbol for TL? Because if you can answer that, either you've seen the periodic table hundreds of times, or you've memorized it. I'm not looking for us to memorize it. Now, last poll question. There are some, yeah, this is one. What is the name of this element? I got to go back. And this is one that, it it will you'll get a little bit more comfortable with it. No, I'm going to give you a periodic table because the one that I'm going to give you has the information that I want you guys to know and that I want to be used as a reference on the exams. Um, Other than that, though, thank you guys for coming to class. The 2 activities are up, the 3 quizzes are up. Um, if you have any questions, I've got office hours. The link's on the homepage. I've got office hours starting at 12:30 today. Join. That does not require your authenticated Texas State user ID. So if anyone from the group me is like, I can never join, say, I think you should try joining his office hours. Um, Other than that, though, thank you guys for coming. Thanks for responding to questions. Great job. And I'm going to add those 2 bonus points on the first exam a little bit later this week. I should have it by the end of the day, or should have it by the end of the week. Thank you so much. Have a great day, everyone. And I will stop my recording right